Bismillahirrahmanirrahim. This video is from chapter number 7 from Mr. Sedra's book, and here we'll be discussing article 7.1.2 and 7.1.3, and also we'll solve exercise 7.1, and this is on the request of a student. So let's proceed. First of all, in the introduction, he's talking about the two types of transistors, MOSFET and BJT, and also he's explaining that the two types of transistors can be used either as a switch or amplifier. So both of them can be used as a switch or amplifier depending on the design parameters. Now, in my previous video, I have explained about the transistor, that is BJT. So BJT, when both the junctions are forward bias, this goes into saturation region, current flows instantaneously in it. And when the collector base is reverse bias, then this goes into active region, and this is the active region where it acts as an amplifier. Similarly, for MOSFET, we had seen or studied this curve earlier. I'll not go into the details, except that it also has two regions. One is called the triode region, and the other is called the active region or saturation region. And so, switch is in this case saturation region, and in this case the triode region acts as a switch, and as an amplifier we have to be in the active region here and also here in the active region or saturation region. And just a point to emphasize that in case of a BJT we have a saturation region and active region, but in case of a MOSFET it's confusing that the saturation region is also called active region and the other region is called triode region. So don't forget this point, that at many places is calling saturation region and many places it is called as active region. Now the next paragraph is to how to obtain a voltage amplifier. Now, before we proceed, these two formulas, I hope you recall. We know the resistance is voltage divided by current, and opposite of it is called conductance. That is, I over V is conductance. So the transistor, whether MOSFET or BJT, is basically a transconductance amplifier. And how is transconductance? Because we are supplying a voltage here and we getting current. So I over V makes it a transconductance amplifier. But more commonly, one is interested in the voltage amplifier, not the transconductance amplifier. So to convert this into voltage amplifier, what we do is we add a resistance here and take the voltage across the resistance or across this circuit as the output. So we have added a resistor here, and now this results in a simple amplifier because now it is the voltage in terms of voltage. So voltage out divided by voltage in. A simple way to convert transconductance amplifier to a voltage amplifier is to pass the output current to a resistor and take the voltage across the resistor as the output. So the output voltage VDS, now this voltage we are calling output voltage, is VDS is equal to VDD, which is the supply voltage, minus drop here, that is ID minus RD. So we'll use this equation subsequently. And similarly, in case of a BJT, we exactly follow the same technique to find the output. Now we'll talk about the voltage transfer characteristics, also called VTC. We have learned this graph for MOSFET. This is called IV characteristics curve, but we will use another curve which is like this. Now this with the two outputs, that is VGS, that is the source voltage, versus VDS, that is drain and source voltage, or this is VDS. So this curve will be called the voltage transfer characteristics curve. Couple of things you have to note here. First of all, this point VT, just in case, as in case of a BJT, you remember that VBE is 0.7 volt taken for the transistor to get on. In case of a MOSFET, we call it threshold voltage. A threshold voltage, VT, when applied, only then this will turn on. So this is the V threshold point. Before this, when this voltage, the applied voltage, is less than VT, then the transistor will not operate. That means it is in cutoff region. So this is the cutoff region. And then when this voltage, VGS, increases VT, goes beyond VT, then the transistor will be in either active region or in triode region, depending on where we stand. So observe that VGS less than VT, the transistor is off and ID is 0. The current through this is 0. And so from the equation 7.3 that we had derived, when ID is 0, then VDS is VDD. What does that mean in the graph? That VDS, this is VDS. This is the point where ID is 0. It is cutoff region. And therefore, this point should be equal to VDD. So this is equal to VDD. As VGS exceeds VT, now VGS exceeds VT, that means we're going here, the MOSFET will be operating in the saturation or active region, and further away it will go to the triode region. Now a point to note, VGS exceeds VT, the MOSFET will be operating in the saturation and active region that we have already discussed. The point to note here is that this will continue until VDS. Now VDS becomes lower than VG minus VT. Now what does this mean is actually, you see this length is VGSB. For if we take B as a reference, then this will be VGSB minus VT. And when this length is equal to this length, or they're equal or slightly VDS becoming lower, that means this is coming lower, that is the point where B will now move, or the transistor will now move from active to triode region. So this point B is the point where it changes from active to triode region. So this condition we have to keep in mind. This is the last limit, we can say, to remain in the active region. So for VGS greater than that at point B, the transistor operates in the triode region. So when VGS moves further here, then it is in the triode region. And the MOSFET operated as an amplifier, its operating point is confined to the segment AB at all times. So this is the active region from A to B. So it has to be, operating point has to be within this A and B. When it is operating in active region, for an NMOS transistor, the current is given by this formula. So we'll be using this formula subsequently. And we have already learned from the circuit diagram that VDS is VDD minus IDRD. Now in this, if you put ID, because we are now in active region, if you put ID, this value, then this is the equation of VDS. So VDS somewhere here, somewhere here, somewhere here will follow this value. ID we have put in the active ID value. So this is a very important equation, 7.5. This will ensure that our transistor is operating in the active region. Now we have to find the coordinates of this point because this is a very important point. And the coordinate of B means the x-axis and the y-axis, which is VGSB is the x-axis value and y-axis is VDSB. Now VGS, this is equal to VGSB at this point, and VDS is equal to VDSB at this point. Also, VDSB is equal to VGSB minus VT. We have mentioned that this and this has to be equal, and this is VGSB minus VT, only this length. So we are subtracting VT, and same value here. So this formula we have learned, and now we'll plug in this into the 7.5 equation that we calculated in the last slide to get the actual value of VDS for the circuit. And the result here will be now from here, sorry, not VDS, we want to get VGS, this point, actually, this coordinate, first of all, we'll find, and then from here we can find the other coordinate. So from this equation, putting these two values and solving, we get this equation. So initially, I was not convinced how to get, but I tried. It was difficult, could not find. So I took help of the AI tool. So MathGPT helped me, and I will not go into the details. Simply what they are doing is that they're making some assumptions. This was the equation here. Now we're taking x is equal to VGS minus VT. So the equation will be simplified, and solving, rearranging, and then further, there was the duplicate. I have removed that. Now this is the equation, and then further we just proceed from here. So this was the equation, and keep solving, we get to this equation. And further solving, this is our equation in terms of VGS over B. So we will use this equation. It is better that we just believe and don't go into the derivation, but it's good for understanding. So this was the result that we got from here for VGSB, this point. There are two alternate ways of writing this. If we take or move VT to the left-hand side, we get this equation. We can write it that way. We also, I hope you remember that VGS minus VT, VGS minus VT is also called V over volt, V over drive volt or over volt. I have explained in one of my videos this point very clearly. VOV is also equal to this, but we'll stick to this formula 7.6 for solving the questions. And also now the second point here, this was one coordinate. The other coordinate is, we can write that VDSB is equal to VGS minus VT, or in terms of VOV, we can write it to be equal to VOV because VGS minus VT is VOV. Now coming on to the exercise, question is, consider an amplifier in figure 7.2a. This is the amplifier with these parameters. So VDD 1.8, RD this. So we can, the first thing we'll do is just change this. We will write 1.8 here, 17.5K. And then it is saying that Vt is 0.4. So this voltage Vt is 0.4. And a constant Kn, which we'll use in the formula, is given. And lambda is equal to 0. That means there is no modulation in this. Length modulation is 0. This is also I have explained in one of my previous video what is length modulation means. Anyway, this will not bother us here. So the question now says part A and B determine coordinates of the endpoints of the active region, the segment of VTC. So endpoint, these are the two endpoints of the active region. One is A and the other is B. So this is first part. And the second part, we have to determine VDSC. Now this point is VDSC, assuming that VGSC, the VGSC here is equal to VDD. So this is equal to VDD and this is equal to 1.8. So the first thing, from the graph, the coordinates of point A are VT and VDD. So this is simple. VT is given 0.4 and VDD is 1.8. So it is 0.4 and 1.8 volt. This is part A. Now part B is GSB and DSB, VDSB. We'll use the formula now. This was the formula that we derived. And we now plug in all the values from here. And solving, you will get this answer. I hope by now you know how to solve it. Very simple. If you take your calculator, go to the mode and select complex 2. So it is now in complex mode. And then you can do all the calculations, although you don't need to be in complex mode here because there is no J terms, imaginary terms. But anyway, using this, so I can write it 0.4 plus, then this is division, so fraction right here, and then the terms like 2 into 4 will ignore this because 10 minus 3 and 10 plus 3 will cancel. So 2 into 4 into 17 into 1.8. So under root 2 into 4 into 17.5 into 1.8. So this is done. Then we'll add plus 1. So this is all within the under root. I will move further, put minus 1. So the numerator is done. Coming on to the denominator, we again cancel these two. So 4 into 17.5, 4 into 17.5. So this is done. Now let's see what is the answer we get. Forward equal sign. This is in not straight form, so we'll just press SD. That is 0.6129 or 0.613 volt VGSB. And now that we know VGSB, this point we can find VDSB by just subtracting VT from here. So VDSB is VOV or VGSB minus VT is equal to 0.613 minus VT is 0.4. So this is the answer. These are the two coordinates of point B. So part B is done, and this is the answer given in the book. So this was the first part, and this is the second part. Now we have to do the third part. Now part C is saying find VDSC, this point, and assume that VGS is equal to VDD. Now, in one of the solutions that is quoted by Course Hero, what they have done is Okay, I'm just writing the value of VDD 1.8. So they have used this formula to find the answer. That is VDD divided by 100. That means they are taking VDSC to be 1% of VDD in the triode region, and they are taking this answer 18 millivolt. But when I tried with the MathGPT, he said that yes, you can approximate to be 1% of the VDD, but I could not get convinced really. Other AIs did not agree, so I took help of another very good AI tool, Monica IM, and I got a lot of help from here. So we'll just follow that. So what is saying that VGSC, this point is 1.8, is much greater than VT, greater than VT. That means 1.8 volt is greater than 0.4. And therefore, we can safely assume that the transistor is in the triode region. Since this is far away, and therefore, from here, the transistor cannot be in the active region, but it has gone to the triode region. So we'll assume that. And what will be the effect of that? And of course, we can verify the answer at the end. The effect will be that our transistor current ID will have a different formula. This is formula for the triode region, or for K dash omega WL, we can simply write Kn. So we'll use this formula. This is the formula that we'll use for the triode region to find ID. And then this is from the MOSFET equation. We get another equation from the circuit, which is, we have already done it earlier also, that VDS is VDD minus IDRD. Now, the only thing we have to do, as we did in the previous case, here we have to replace with this ID in the triode region also to solve. So these are the two equations. Putting the value of ID in here, this will become our equation. Now we'll plug in the values. And since this unknown VDS, here also VDS, here VDS square. So we have to find this. Apparently, when we simplify, as we have done here, this becomes a quadratic equation. We have to solve the quadratic equation. This is the quadratic equation that we need to solve. And if you use your calculator in equation mode, you can directly get the answers. Let me show that. Calculator mode. We go to equation mode 5, and the quadratic is just 3. And now he's asking for the parameters. So the first one is 35, parameter of the x square. We write 35, equal sign. Next parameter is minus 99, equal sign. And the constant is 1.8. So 1.8, equal sign. So we have entered all three values. Now we press equal. So we get x1 to be 2.81. And the second root, we again press equal sign. The second root is 0.0183. So 0.0183. So these are the two roots that we found from this equation. Now we have to rule out one of them, that 281 is impossible, since VDS has to be less than equal to VDD. Now this value VDS, wherever we are, it has to be less than VDD, and VDD is 1.8. That means VDS has to be less than 1.8. So 2.81 is not possible. Therefore, the other option is the only option available. So we'll take this as an answer. VDS is 0.183 volt, equal to 18.3 millivolt, and we can approximate it to be 18 millivolt to match the answer given in the book. So this is how you solve. Now, those of you who are keen to find out or verify the assumption that we had, that we are in the triode region, we know that for active region, this VGS minus VT is equal to VDSB, this. But when we move here, then what will happen? The condition for the triode region is that VGS, now VGS is somewhere, so VGS minus VT, VGS minus VT is this area, VGS minus VT is this area. It has to be greater than VDSC. Now the VDSC has come here. Based on this, the vertical axis is here. So this is, or this has to be greater than VDSC. Now let's put in the value. This is 1.8 VGS here, 1.8 minus VT is 0.4. So VDS has to be less than 1.4. Now the VDS that we calculated was 18.3 millivolt, which is of course less than 1.4 volt. Therefore, our assumption is correct. I hope you have been able to follow this. Please let me know through your feedback. Thank you. This confirms that the transistor is in the triode region.